Hello. In this video, we'll be continuing with the series on current electricity, and as I had referred in the previous video, at the end of the previous video, that we'll be trying the mixed grouping of cells. So here's the mixed grouping of cells, and from that we'll be obtaining the condition for maximum current. Now in this case, if we have cells, and as considered earlier as well, we'll be uh, taking equal EMF and internal resistance for each cell, and let there be, supposedly there are n number of cells which are connected in series, so each cell having an EMF E while an internal resistance is R for each of them. So like that, we have n number of cells to be connected in series, and we have m such rows. So m such rows for n number of cells connected in series. That means we connect them parallelly. This is the second row. Likewise, we are having the same number of cells in series with the same EMF and internal resistance in each case. We can just fill in the space between with dots representing the cells. So these are the arrangement of cells, and here we have m rows. So m rows, and n can be here treated as the column. So m rows and n columns of cell, each having EMF E, internal resistance R. So the total number of cells, that are there, let that be equal to capital N, which is equal to m multiplied with n, obviously, because we have m number of cells arranged column wise in each column, and we have n such columns. So m being the rows and n being the number of columns, and this entire thing is having an external arrangement with an external resistance R, and obviously we'll have some current flowing across the circuit. Now the potential difference, obviously, across these 2 points, let these 2 points be A and B, the potential difference will be the same, because we are considering, or we have taken each cell to be having the same EMF and internal resistance. So obviously across each wire that we have considered over here, each wire will be having the same amount of potential difference, and we can just check it for ourselves. Each wire has n number of cells, each cell has an EMF E, and they are all aligned in the similar sense. So the potential difference across AB, or the net potential, so as to say, net potential difference that we are obtaining, that is equal to, we take it as E net, and E net here is n times of E. Now that being the net potential difference, what is the net resistance, which can give us the net current flowing through the circuit? Now the net resistance across the given circuit, across each wire that we have for parallel combination, the R being the internal resistance, n number of such resistances internally are in series, so net resistance across each row will be equal to n times of R. But that is not all. N times of R, but we have m such columns, means m parallel combinations. So nr being the resistance in each row, with m such columns, we can just divide it with m, and this is what we had learnt previously while we were doing the combination of resistances, just the previous video. And but that is not all. This entire resistance, internal resistance thing, this has to be added to the external resistance that is provided in the circuit, and that is in series with this entire arrangement. So the net resistance, we can say it as R net, that is simply equal to NR by M plus the capital R, which is the external resistance. Now the current, obviously using these two, we have I is equal to the net EMF divided by the net resistance, and that obviously goes to N times of E divided by NR divided by M plus R. The M can be taken as the LCM in this case in the denominator, so we have NE divided by NR plus MR, but the M that stays there below, taken as the LCM, that can go up and get multiplied over here. But what we know about M times of N over here is that M times of N is simply equal to capital N, the total number of cells. So this is N times of E divided by NR plus, this is capital R, so NR plus MR. This is the total current that flows across the circuit. Now this is the expression for current, but hang on. I had also mentioned that we will be obtaining a condition where we can get this current to be having the maximum value. Now in order that the current has a maximum value, the denominator term NR plus MR, that has to be reduced, but we can reduce the denominator to 0, but they are getting added, so obviously they cannot go to 0. Nm small r, capital R, the internal resistance and the external resistance, they have finite values, so that can never go to 0. But however, we can obtain a condition where we can have a reduction in them, and let's check for that condition. Now that is to obtain the condition for maximum current. But for that, the term NR plus MR must be minimum, or must be minimized to the maximum extent. So we can just consider this in this way, that is NR plus MR. How about taking this as root over of NR plus root over of MR, right? And we take the square of it. Actually, we just take the minus of it and then we square it off, but that will be equal to the left hand side, provided that we have a term which is 4 times of root over of NR root over of MR. Hope you're getting the hang of it. This entire thing that we have over here, this is NR plus MR, simply is equal to the root over of NR whole root of NR plus MR squared. We can just represent it like this on the right hand side that I've just written. Let's just check that out if there's any mistake in writing it in that form. If I open the brackets over there, I have NR plus MR minus 2 NR MR. Okay, so this is 2 over here. Now I'm completely correct. If we are to open the bracket over there, we have NR plus MR minus 2 root over of NR times of MR, root over of MR, plus 2 root over of NR plus multiplied with root over of MR that is present over there, and that gets cancelled out, so the LHS and RHS becomes the same. You can expand it this thing for yourself and check it uh, for your clarity. So just a minus b whole square in that form, you expand it and then just add it to the right hand side term, this term, and you end up with this. So this will definitely be minimum with this minus thing available. This minus thing, however, can go to 0. Now this will be minimum if NR, root over NR minus root over of MR is equal to 0, or simply put it as root over of NR is equal to root over of MR. Get rid of the roots now. NR is simply equal to MR. With that available to us, we can just relate them. So whenever we have NR is equal to MR, or we can say that the external resistance is so selected that it is just the ratio of the number of columns to the number of rows multiplied with the internal resistance. This is going to give us the maximum current, because this is the condition where the denominator term in this expression is going to be minimum, and with the denominator being minimum, obviously the left hand side carrying the current over there, the expression of current, that maximizes in this case. So this is definitely the condition for maximum current that we have that we were to obtain. You can take examples. We'll be doing a few examples in the numerical section of the current electricity part, so that's for the other videos to follow. But as of now, theoretically speaking, this is the condition for maximum current. Now obviously we can measure the efficiency of a cell that has been provided to us for across a given circuit. Now the efficiency of a cell, usually represented by, denoted by the symbol eta over there, is simply the output power, useful power that it is providing to the circuit, per total power developed across it. Now the total power developed is obviously uh, comprising of the power developed across the external resistance as well as the internal resistance. However, the useful power that we are getting is simply is equal to the power across the internal external circuit, that is I squared R. I squared R being the expression for electrical power. This divided by the total power that is developed is across the external circuit as well as the internal resistance that is available in the cell, which is where the current is obviously the same because of the series combination. So in that case, the I squared terms in the numerator and the denominator taken common can get cancelled out, and all we are left with is simply the external resistance divided by the sum of the divided by the total resistance across the circuit. Or we can just put it in another way, that is 1 divided by 1 plus R divided by R. This is one way of writing it. So this gives us the efficiency, the expression for the efficiency of a cell, uh, that is provided across a given circuit. Then we are done with the current and the resistance part and the cells that are involved in a circuit. Now we'll be learning about a few rules or laws that govern the the working in a particular circuit. And the first and foremost law at this level that we are to learn are the Kirchhoff's laws, the Kirchhoff's current law, as well as the voltage law. We'll be doing the current law in this video. The voltage law will be followed in the next video, uh, uh, keeping in mind the length of the video that I usually uh, make. So starting off with the Kirchhoff's law in electrical circuits. And the first and foremost law that we come across is Kirchhoff's current law, or simply written as KCL. It is even referred as the junction law. Now, the junction law obviously relates to the junction in a given circuit. Let us say that we have a point where the wires that are drawing current, they are entering into a junction, popularly also known as the node point, nodal point, and you have wires drawn out of that point. So this is I1, I2 and I3 are supposedly the current that are entering into the wire, or into that junction point, that is J. And from that you have I4 and I5 as the currents coming out of that point. Now this law, this statement, it states that the total amount of current that is associated with a given junction has to be equal to 0. As simple as that. Because the current never sticks or never stops at the junction, it flows completely. The current that has entered into the junction must exit out of it. So the junction never keeps any amount of current within it. Neither is there any new current developed in the junction which adds to the current that is going out of it. So obviously there is no current to remain in the junction. So the net current associated with the junction is equal to 0. Now this is obviously on the basis of conservation of charge, because the current obviously is due to the flow of charge across a given circuit. So this is on the basis of conservation of electric charge. And this conservation of electric charge, it states that charge can neither be created nor be destroyed. So obviously there is no creation or destruction of any amount of charge as the current goes past through that junction, and that is why there is no loss or gain, or there is nothing, no imbalance created. So as a result of that, the amount of current entering has to be equal to the amount of current that is getting out of it. For that, in order to explain that simply, we follow a sign convention. Now this is just a convention. It can be reversed, as I would be explaining a few moments later. the thing that we consider, the convention that we take, is that we take the current entering into the junction, current entering into here, the junction taken is J, so I'll take it as J. So the current entering into J is to be taken as positive, while the leaving current leaving J is to be taken as negative. We can, however, take it the other way round. That is, we can take current entering as negative, current leaving as positive. That won't really matter, as we are going to see in a few moments. So we just take the summation of the current that is associated with that junction. That is what we have written over there right at the top. So the summation of all the current that is associated with the junction that we have taken in the diagram over there is that I1 plus I2 plus I3. Now I1, I2 and I3 all are taken as positive because they are entering into the junction. Then we add up the negative of I4 because it is leaving the junction, and so does the current I5, and so, but they are added obviously because we are summing it over. However, the sign conventions are that they are to be taken as negative. This entire thing goes to 0. So finally what we have is I1 plus I2 plus I3 is equal to the I4 and I5 can be taken to the other side, which also means that the total amount of current that is getting into the junction is equal to the total amount of current that is going out of the junction. This is another way of stating the Kirchhoff's current law. Or we can say this is the current law and this is the junction law. Both are the same things obviously, but the interpretation is obviously a bit different when it comes to the definition part or the statement part of it. Both these statements obviously mean the same. You can use one of those formulas, that one of those expressions that we have just written over there, but they will obviously complement each other uh, as we proceed into the circuit. Right, so the total current that is entering, or that is provided to a junction, is equal to the total current that is coming out of it, because there is conservation of charge. There is no loss or gain of any form of electric charge at the junction or along the wire. Had we reversed the sign convention over there, that is, current entering will be taken as negative and the current leaving as positive, it wouldn't have made much of a difference, because as you can see that if the I1, I2, I3 had minus signs while I4 and I5 had positive signs, then just taking one of the negative terms to the other side because of the zero available there, it would have ended up the same way as we have ended up right now. So this was the Kirchhoff's current law or the junction law. We will now, this is a part of a circuit obviously, because the circuit may carry a junction, and in that junction you may have the current entering and leaving. We will have more clarity about this current and the junction law as we proceed in the towards the Kirchhoff's voltage law, but that is in the next video. The Kirchhoff's voltage law that is to be explained, that will be in the next video, and after that we'll be applying Kirchhoff's law to the Wheatstone's bridge and its balanced condition. We'll be obtaining its balanced condition and using that balanced condition as well for meter bridge and other types of circuit as well, potentiometer likewise. But that is for the next video. Till then, thank you for watching.